In this video, we're going to study the free particle solution that we obtained in the last few videos. As we can see here, we have an integral in our solution over some range of k values, and then we have this phi of k to denote that function that determines the amplitude for each of those values. So now we have a range of energies, and as a result, we need to be a little more careful in how we interpret other features of this wave, like the speed, namely, which is what we're going to go over in this video. So if you wanted to ask what's the speed of this wave, or any traveling wave for that matter, what you do is you take the coefficient next to t and put it over the coefficient next to x. So in that case, we're going to get omega over k as the speed. And you might be wondering why you do that. Well, I think it's easier to see if we just rewrite this wave by pulling out the k from the parentheses here. And we get x minus omega over kt. As we can see, the coefficient here is what we have for the speed. And what this says essentially is that every second that passes, our wave is going to shift some amount omega over k. And that's exactly what we mean by the speed. So that's how you would interpret this. And now let's look at this value a little more closely. So we can plug in what we mean by omega, which is k squared h bar over 2m. And the k is going to cancel. So we just get k h bar over 2m. And then plugging in our value for k, we have the h bars are going to cancel here, and we get 2m times the energy over 2m, which is just square root of the energy over 2m. And this would be all right, except it's actually incorrect if we relate it to what the energy should be classically. We don't really want any disagreements there. The actual speed of this wave should match what we would find from the classical equation relating energy and the speed, which in this case, since there's no potential, we just have that 1/2 mv squared is equal to the energy. And if you just solve for the speed here, what we should get is actually 2 times the amount that we find up here. So evidently v quantum, which is the quantum speed we calculated, is 1/2 v classical, which is a bit of a contradiction. So we want to find a new way to interpret this, and one way that we can recover the classical speed of the wave. So the approach that we're going to take is that we want to look at this wave function here and take out and separate the different expressions for the individual phase velocities of those specific k values, and the actual velocity of the entire group of k values, which is where the confusion arises, because right now what we're looking at is just the phase velocity. It's like we're saying what's the speed of this particular wave at some value k, but that's not quite what we want. We actually want whatever encompasses that entire range of k values. That's where that information is contained in this phi of k function. And just as a kind of aside from the last video, we interpreted this phi of k as being the Fourier transform of our psi function. So that's kind of interesting. But anyways, so let's make things a little easier on ourselves and imagine a kind of nice function for phi of k, where the momentum, or this energy, has a nice distribution where the actual energy of the particle is well defined. And the best way we can do that is have it be narrowly peaked at some particular value, which we'll call k naught. So let's say k naught is here, and this represents the amplitude. So we can imagine a function that looks something like this. And this is nice because this gives us a really nice, well-defined momentum for the particle. And if the wave was more diffuse, it would be harder to actually say definitively what its speed is, so we might as well consider this case anyways. And this has the property that outside of k naught, the function pretty much evaluates to 0. Now, given that phi of k looks like this, and the amplitude of k is pretty much 0 everywhere outside of k naught, what we can do now is think of omega as a function of k, because it is. It's k squared h bar over 2m. And we can Taylor expand this at the point k naught and drop everything but the leading terms. And this will give us a very good approximation for omega. So first, let's just say omega naught is equal to omega k naught. And then if we expand this, we get omega naught plus omega naught, the derivative at that point, times k minus k naught. And this is a very good approximation for omega of k. Now we can replace this in our integral and see what we get. So we have 1 over the square root of 2 pi, the integral here, and then minus omega naught t minus the derivative of omega naught, k minus k naught t, and this is our new wave function. And now we can make a change of variables here to make things a little easier. So we'll say s is equivalent to k minus k naught, and note that ds is equal to dk. So if we make that substitution, we have phi of s plus k naught e to the I, and then sx plus k naught x minus omega naught t minus the derivative at that point times k minus, or times s. Oops. So now, this is ds. Now we can pull things out of the integral that don't depend on s. And here's where we'll actually make that separation between the individual phase velocities, which we calculated earlier, and the actual group velocity, which is the entire range of values. So the ones that we can pull out in particular is this value and this value. So if we pull that outside of the integral, here we get this term that looks like will give us the velocity we had from before, which is good because it's for a specific k naught value. And then inside this integral is where we're left with the actual group velocity, which in this case is represented by this exponential function. And what happens if we take the coefficient here and put it over the coefficient here? Well, that's going to give us v, I'll call it v group, is equal to omega naught prime, and we don't need to call it omega naught anymore. You can just say omega prime, which is the derivative, which is, well, the omega, first of all, is k squared h bar over 2 to the m. So if we differentiate, we get k h bar over m. And now plugging in the value for k, we have 2m times the energy over m, because the h bars cancel, and we're left with the correct velocity. Oops. which is 2 times the energy over the mass. So that's the group velocity of the particle, and it matches the prediction we would get classically, which is good. So this is the end of the free particle series, and in the next videos, we're gonna look at the Dirac delta function. Thank you.